Okay, so this is going to calculate flux. It's going to bring basically everything we've ever learned into one problem. It's going to be pretty crazy. Okay, so this equation defines a surface. And that surface is the graph of z above the unit square. And then here we have a vector field, and we want to compute the flux through S. Okay. So first a picture. So here's our surface. It's going to be somewhere in space. So here's maybe x, y, z. And somewhere is the unit square, above the unit square in the xy plane. And so we have some surface up here. Some surface. Which, this is the surface. And, well, it's defined by this equation. So really we can actually think of, there's a function c, I don't know, I'm calling it c because for constraint, that just sends a point to z minus x squared plus y, or also c for contour, so that, and maybe I'll write in words, our surface S is the zero contour, or the zero level set contour for C of this map, C. Okay, so whenever this equals 0, those are points on the surface because of this equation. Okay, now that's helpful because at a point on this surface, let's say it's P equals x, y, z, then we will need the normal vector. This is supposed to be the normal vector at 90 degrees with respect to the tangent space there. And that will be, well, we can get that from the gradient of C. So it'll be the gradient of C at P will be normal to the surface. Or we can normalize it by just dividing by its length. Okay, so you remember the gradient of a contour is orthogonal to the contour. So that's this sort of thing here, where we get 90 degrees. Okay, but then also we have some vector field at that point. So I'll draw another arrow. This is our vector field, capital F, and it has an I hat component and a k hat. So let's see what it is. It would be, z I hat plus, there's no j's, so that's a 0 there, and there's an x in the k direction, so like that. This is a vector field. Okay, and then we're even going to have one more function. This is the function that is going to give us the flux. I'll call it little f, and it's the function that sends a point P to the dot product of the vector field at P with the unit normal at P. So the normal, in other words, it's going to see these two vectors, this normal vector and that vector field. How much are they going in the same direction? That's sort of going to measure how much is our vector field fluxing through the surface P, through the surface S, well, at the point P, and then we'll integrate over all the different points on the surface. And so I have the vector field dot product with the unit normal. The unit normal, gradient of C at P, is a vector, and just scale it down until it has unit length. So we just divide by the length of whatever that vector was. Okay, and you see that little f is a function. It takes a point P on the surface, and it spits out a real number. So notice, this is a very heavily labeled picture. It has gradients and contours, which is, we looked at even problem 1 through 3, and then gradients in the derivative section, and that will give us our normal vector here. And then we take the flux is the dot product of our vector field with the normal vector to see how much it's going through our surface. Okay, and now, in order to actually compute this integral, this is a curvy surface, but to compute the integral, well, we need a parameterization map, G. And in this case, it's very easy to see what it is. In fact, I'll even just keep the same variables, x and y. It just takes this unit square and puts it to this surface. How does it do it? Well, it does it by, okay, so let's write the formula for G. This is G, and it sends it to what point? Well, x goes to x, y, and then x squared plus y. Do you see what I did here? So that's a parameterization map. We're actually parameterizing the surface. It's a curvy surface, but we're parameterizing it by the unit square below, okay? Which we can just draw over here again. Okay. Excellent. So we want to integrate this function over this surface, and we'll do that by pulling it back here. But that means we need, volumes are distorted. When you go from this nice square up to this curvy thing, you are distorting volumes. And so we need to right away compute square root determinant of gram matrix. And so we need W1, well, the gram matrix of, well, there's 2 input variables. So we'll have 2 columns of the Jacobian. W1 will be what? Well, x derivative, x derivative, x derivative. W2 will be what vector? Y derivative, y derivative, y derivative. I hope you agree with my derivatives. Okay, well, that's not too bad. I can take some dot products now. W1 dot W1 is 1 plus 4x squared. W1 dot W2 is 0 plus 0 plus 2x. W2 dot W2, so that means we have a 2x down here. W2 dot W2 is 1 squared plus 1 squared. So I need to take the determinant and then the square root of all that. Okay, so the determinant is 2 times that, and then minus 2x times 2x. And then I need to take the square root, and this is finally the square root of, okay, 8 minus 4 is 4, and then there's a plus 2. Okay. So great. This is my change in volume factor. Okay. Excellent. So maybe I'll just put that in a thought bubble. I don't know why this helps me organize. Okay, so great. So now we've found out how does G distort volume. It's by this factor. All right, we're ready to integrate. We just need to integrate this function over the surface. Well, that means we need to pull it back to here, and we'll integrate f over g. So in formulas, I'll say the flux is equal to the integral over our surface of f. F is this function. It measures how much the vector field goes through the surface in the normal vector. It measures that by a dot product. And we're going to pull it back to just go from y equals 0 to y equals 1, x equals 0 to x equals 1. And we have to account for the distortion volume, which is square root of 4x squared plus 2. And then times what? Well, f after g. F after g. Okay, so now we need to figure out what this is. Okay, so we can do that. first, let's compose, okay, so we need the vector field, and so we need to compose first the vector field with G. So let's do that. Notice that the vector field, since this is capital F, it goes to Z, 0, X. And so if I string these together, I get x squared plus y, 0, x. Okay, so this is capital F after G. Okay, so that's what I'm going to put here. And now I need the gradient and to normalize the gradient, so I can, maybe I'll go over here and compute the gradient of C at the point P is going to be, okay, so negative 2x. Now I take the y derivative. You have to remember gradients. Do you remember how to do gradients? I hope so. Then I take the z derivative. And that gives me a vector. And now what's the length of that vector? Well, it's going to be dot product with itself, 4x squared plus 1 squared plus 1 squared. Well, that's 4x squared plus 2. Oh, and this is the length, so I need to take the square root of the dot product of it with itself. Okay, so great. Interesting, because look, this is identical to this. That is good. So now this thing right here is just going to be the gradient divided by its length. So that's just going to be the gradient divided by its length. So I'll just do 1 over square root of 4x squared plus 2. Okay, this is a vector times a number. I'm just scaling it down. Of course, I could write this in every single of the 3 components as a divided by, but I don't want to do that, so I just put it out here. Okay, so then this dot product here, this dot product is going to be equal to the dot product of, okay, we computed f of p. It's this thing. Remember this thing? We strung together the vector field with the parameterization map. Composed functions, x squared plus y, 0, x. There's a vector. Now my second vector is here. This is the normal vector to the surface. Minus 2x, 1, 1. And then there's this 1 over square root of stuff. Okay. So then this becomes, okay, well, 1 over square root of the stuff times, now I take the dot product. This plus this, or sorry, this times this plus 0 plus x. Plus 0 plus x. And so at the end of the day, I get, okay, minus 2x to the third. Now, y times minus 2x is minus 2xy, and then I have plus x. Okay, great. And then all of that is divided by square root of 4x squared plus 2. But now look, I mean, so this piece goes here. So this integral becomes integral. This cancels that, and I just get minus 2x to the third plus x minus 2xy. I don't know why I switched the order of these. It doesn't matter. Okay, so let's do this. X equals 0 to x equals 1. Y equals 0 to y equals 1. Why? Because we had the unit square and its graph of this function, z. Okay, so now what's h of x? It should be x to the 4th over 4, and the minus 2 hangs things around. X becomes x squared over 2. Minus 2xy becomes minus 2 x squared y over 2. Okay, so this is minus x to the 4th over 2 plus x squared over 2. And then these 2's cancel, and I get minus x squared y. Okay, so now I do h of 1 minus h of 0. Okay. Minus 1/2 plus 1/2 minus y. Okay, so first integral is done. Fundamental theorem of calculus one time. Now I need to do it a second time. Y equals 0 to y equals 1 of y. Here, h of the fundamental, the antiderivative is easier. Y squared over 2. That's the answer. The flux of this vector field flowing through the surface, adding up all these little dot products of the normal vector with the vector field at every point in the surface weighted by volume, is equal to 1/2. Wow, this is a great problem. It has basically everything we've ever done. Dot products, gram matrix, determinants, lengths of a vector, normalizing a vector, vector fields, functions, contours. This is a wonderful problem. Take your time with it.